So our first speaker this afternoon is Dr. Thrish Nanayakkara from Imperial College, where he is the director of the Morph Lab. So Thrish, do we have you here? Are you able to start sharing your slides?
Yeah, I'm here.
Amazing, brilliant. Well, I will
let me share my screen.
Brilliant. And then I will hand over to you for the first screen.
Do
Brilliant.
you see my
Okay,
screen?
so over to you, Thrish. Thank you.
Great. Thank you, Jesse. Um, yeah, I'll talk about shared computation between the brain and the body. So on your left, so you see this. The ear, in our ear, we have this cochlea solving a computational problem of mapping time domain pressure waves to frequency domain signals, right? And the brain knows only in the frequency domain. So this has to be done real time. And then due to some reason, this responsibility of mapping time domain signals to frequency domain signals has been delegated down to the physical structure of the cochlea, and then the brain takes from there onwards. And then in the middle, you see somebody riding a bicycle on a bumpy terrain, and then you see carefully. So the brain asks the body, the knee joint, to come off the seat and then have a bent knee and ride the bicycle, so that the bent knee can work like a shock absorber and then filter out unnecessary information for riding. So it is more like the brain is really delegating the responsibility of filtering unnecessary information, and then just focus on the task relevant states. So on the far right, you see the cerebellar mechanisms of climbing fibers that build these predictive models, so that you can predict the consequences of the motor actions, sensory consequences of motor actions before they are sent down to the muscles, because there are communication lags in these neural circuits. So the whole intelligent behavior falls into one of these three categories, like fully physical computing, like the ear, and then the brain conditioning the body to solve some problem, while brain focusing on a task, some kind of a multitask, and then the brain doing more model-based control, right? And then, well, I want to make some observations. One is that no matter how complex the world is, right, or the task is, the present moment is always simple in terms of dimensionality, right? Take that, let's say, bicycle riding task. So if you think about that whole bumpy terrain, it is complex. But at any given moment, if you focus on a very small time window, it just has to focus on a single dimensional control command, right? So maybe just to move the joint by some delta amount. So this means that an agent can be very smart by fine-tuning real-time computation to deal with the minimum number of state variables within tight computational deadlines, right? So if we can achieve these deadlines of computation, then it can focus on very low dimensional problems that can be solved within small quantums of time, and then it can focus. And so the whole problem is very complex, but in finite simultaneous small time window, the problem is very small. So that means that you can have bodily posture and impedance control variables, let's say the stiffness of the joint or the posture of a joint, and the movement and force variables, uh, joint speed and joint acceleration, or the force variables. If they can find a strategy to concurrently control the body posture, impedance, and the movements, then it can focus on this free energy problem. So it has to minimize the error of states. But if it is in a very small time window, these dimensions of these states are very small, and then the error vectors are also very small. And then the next problem is to meet the computational deadlines. Sorry, computational deadlines. It has to quickly reduce the entropy of these states, right? So that we call observation problem. So if it can do something to control zeta and phi, and then gain information as fast as possible, and then it can deal with this control problem in a reduced dimension in a small time window, right? So one example I'm giving is this one of my PhD students, Xing Tang's work. So he developed this soft sensor skin under the orthosis devices, so that he can monitor the pressure developments under orthosis devices, so that the hospital can know the excessive force developments and discomfort levels, and so that they can remotely release those pressures. So we developed this sensor, and then he wanted to really focus on the contact force, not other forces coming from hand movement and all these shear forces coming from there, right? To how to insulate or how to isolate this sensor from other task irrelevant information. So he thought about this fish scale type mechanism around it. So if you have the right fish scale gradient, you see the stresses, local stresses around the sensor are very low. And if you have, a different structure, there are local stresses coming from task irrelevant movements and interfering with the task of monitoring the orthosis pressure. So if you can really focus on the task relevant information and then have a physical mechanism that can take out other task irrelevant states, then the task becomes very simple. So this is a pure physical solution, but it can be that the brain is, let's just imagine these the sizes or these gradients can be controlled real time. Maybe you need this kind of uh, scales for another task, and then you need this gradient for another task. So if the brain can go between back and forth these structures, then you can do very dynamic tasks, right? So this is a special situation. So if I go back to that knee joint thing, so Ilham Hamid, my PhD student, she worked on understanding what the knee joint is doing in terms of computation. So what we see is that the angle, there's an angle dependent damping profile in the knee joint, right? So around 20 degrees or 30 degrees, there's a maximum viscosity in the knee joint, and then above and below it drops out. So that means there is a gradient you can use to move your bandpass filters just by controlling the knee joint angle, right? So when you land on something or you collide with the ground, you might want to have low damping, right? So that means you increase your knee joint angle, and then you reduce your damping, and then when you're walking, you are roughly walking in this range, right? So and then she tested this hypothesis that by having the right shape of angle dependent damping profile, it is really simplifying the world for the brain, right? So she implemented this hyperbolic damping profile, which has a eta control parameter, and then it has a base level damping, right? And then she looked for the best level of eta that can give the maximum filtering effect. So what she found out was, so for if you have a hyperbolic, that kind of angle dependent damping profile, you can significantly reduce collision forces, right? Collision forces relative to a flat damping profile, not angle dependent damping profile, at the peak level or at the base level. So the medium level, which is what I mean by peak is that top value, so this top value, and then mid is the medium value. So but it is flat medium, flat peak, and then versus this kind of a angle dependent damping profile. Just by having that profile, you can reduce collision forces, and you can have a reduced displacement after collision, and then you can have reduced entropy of collisions, right? So that this really simplifies the task of uh, controlling collisions, like so walking, for example, or touching something, manipulating something. So this really is an important thing. So that means the brain can take control over the angle of the knee joint or any other joint, and then take advantages of its angle dependent damping profile to simplify the task. So another example is Sarah's work. She found that this mountain goat hoof, right? So if the mountain goats slip, they don't have a chance. The brain doesn't have a chance to react because it might be too late by the time the brain knows about the slip. So she found out that the stiffness configuration among these three joints is a key to maximize dynamic slip reduction, right? So if you have the stiffness combinations in the right domain, you have stick and slip type, like a ABS system in a car, right? So in a vehicle, you cannot stop the vehicle by having static friction. So you can stop it by having chopped friction. So that is exactly what the hoof is doing. So by having the right passive dynamics in the hoof, it breaks it on its own using the passive dynamics. So you can see this. Um, so if you have the compliance at the gamma, beta, and theta, so you need to have a low compliance in the interdigital ligament, and then high compliance in the other 2 degrees of freedom, so that these vibrations can be magnified in the hoof itself. Um, so this is again valid in other manipulation tasks. Like for example, if you go to a GP, the GP would examine the abdomen, and then while doing so, they will condition their posture and the stiffness of the fingers, right? So why do they have to do that for a perceptual task? The reason is your tendon sensor and your spinal sensors are part of the actuators, the muscles, and then by taking control over these muscle tensions, you can take control over that zeta parameter I mentioned, right? So the zeta is the stiffness of the body, and the phi is the behavior of the fingers. And then by doing so, you can gain information, right? So that if you can move from zeta 0 to zeta and phi 0 to phi in your behavioral parameter and posture and embodiment parameter space, if you can sharpen the probability distribution from its initial contribution, so distribution, then you gain information. So just by conditioning your the body, you can gain information and then reduce entropy of state variables rapidly, so that you can meet deadlines in those small time windows, right? So we independently tested this hypothesis in robotic fingers. Uh, like we just had a very simple approximation of the finger stiffness control mechanism by just pushing and pulling a carbon fiber lever. And then by doing stiffness control, we saw that how the robotic finger tendon feels a tissue condition, like a nodule buried in soft tissue, is different. And then it changes from the direction of movement, and then it changes depending on the stiffness too. So in a Bayesian information gain framework, so what that means is you can take control over the likelihood function. So no matter what the prior distribution is, if you can take control of the likelihood function, if you can see here, just by controlling the stiffness, you can control the shape of the likelihood function, so that your posterior converges to the true value rapidly. So this way, so if you by conditioning your body, you condition the likelihood function of perception, And then that way you converge faster to random variable estimation that allows you to stay present or stay real time in computation. That way you can just focus on one variable at a time and then still deal with a very complex situation, right? So another observation is Lisa's work. So she looked at the phi side of it, right? So I talked about the zeta side here, right? So this is the zeta of that. Zeta is the body variable. Zeta is the impedance of the body. Phi is the behavioral variable. So Lisa looked at that side. So she looked. She put a force sensor underneath the soft tissue and they looked at what kind of force profiles people are exerting. And then she saw that there is a 20 hertz sinusoidal signal in lateral forces of people when they examine nodules. And then what that is that significant? The significance is like we tested that in a robotic finger, and then she saw that if you have that around 20 hertz sinusoidal signal, if there is no nodule in the tissue, the tissue liquefies under your finger. So you feel it softer than what it is. But if there is a nodule, you feel it harder than what it is. So that means just by taking the right behavior, you are conditioning how the fingertip feels by magnifying information. So we call this behavioral lensing effect, right? So you can see that. So this means this is our collaborations with Josie and Luca. And then what they saw was that it's similar thing, right? So just by um, taking control over the behavior of palpation, the fingertip sensors and the tendon sensors uh, will feel the same thing in different ways, and then they can maximize information gain by having the right behavior of palpation. So in this case, they control this kind of a 3D space movement, Rx, Ry, and then the Z position. So by having different profiles of palpation, you improve perception. So these days
Sorry
we
to
are.
interrupt you. Sorry to interrupt you, Thrish. If we could just wrap up on this slide, then I think we might have to go on to the next speaker. As lovely as it is,
Right. Okay, sorry.
we'll follow up discussions later in the
Yeah,
panel discussion. So
yeah.
thank you.
Sorry. So this is about during palpation we give visual feedback from different facial expressions from different ethnic and gender backgrounds. So this is again adding another variable for the task. Um, yeah. So I will wrap it up. So the concluding observations are: no matter how complex the world is, the present moment is always simple, and then that means the brain can take concurrent action to both condition and control the body to meet real-time computational deadlines and to minimize task-relevant errors. Thank you.
Thank you very much, Thrish. And I'm sure we'll come back to discussing many of these things. So thank you. That was a really interesting talk.